So, now that I've talked about L2s and covenants, now that you're dragging me back in again, I'll go and talk about single-use seals and client-side validation and all this. And curious, how many of you people have heard of RGB? Come on, it should be all hands. RGB is made by Ukrainian devs. All right, so the idea behind, like the big idea behind RGB is client-side validation. And as the name suggests, client-side validation says, well, why don't we have the client who's actually participating in some system validate the data associated with the system? And I'll give you a thought experiment. You know, of course, in Bitcoin, we have proof of work, we have a blockchain, and we have block validity rules. And the block validity rules say things like a transaction has to have these bytes in it, it's got to be in this form, you know, signatures got to be valid, et cetera, et cetera, et cetera. Now, hypothetically, what if the Bitcoin protocol only had the proof of work rules, right? What if your nodes did exactly one thing, which is they exchanged blocks of data and looked for the highest, you know, the most work on those blocks of data? Would your nodes be able to come into consensus?
Yeah, why not?
Exactly, why not? Right? But, you know, we're not talking about SPV node here. We're just saying, what if Bitcoin had no rules except for proof of work? Now, if you ignore the economic side of this, from a tech point of view, certainly this could work. We could all come to consensus. We could all decide what is the valid chain. Now, it might be a little useless because we would decide what is the valid chain over arbitrary data, but we could come into consensus. Well, how do we make this more useful? Well, what if we have a second layer on top of that, which then implements rules, right? What if you just took Bitcoin as it is and took all of the transaction validity rules and just applied them to the random data that you're coming to consensus to? You could make the rule be, if it's a valid block, we process the validity rules and update the UTXO set. If it's an invalid block, we do nothing. Now, could you trade Bitcoin with such a system? Of course you could. It might be a little weird because sometimes blocks would be invalid and they would be meaningless and you wouldn't really know why the hell did they spend so much money making the block, but it would work. You would have lower level consensus and upper level of validity. And I would argue such a system could even be bootstrapped, because provided that everyone, or at least most people, agreed on a set of consensus rules for transactions, the economics to make the blockchain move forward could still work. And this concept is something I wrote about like in 2013, you know, deconstructing how the hell block, you know, validity works, et cetera, et cetera. It's on my blog at the very bottom of the list. But I would argue this is a good way of thinking about Bitcoin. Now, I would call such a system a client-side validated, but it's not a very efficient client-side validated system, right? Just like Bitcoin, you still got to process the entire chain. Well, you can imagine systems which are a bit more nuanced than that. Like especially, you know, a lot of systems where you might want to have consensus over something, often the thing you have consensus over doesn't have very deep history, right? Imagine, for instance, if you're talking about a consensus system for like real estate sales. I mean, how many times does like a chunk of property actually change hands in 100 years? You know, it might get sold, what, at most 100 times for a truly bizarre situation where like someone's spying and selling houses over and over and over again. Well, 100 transactions deep is not very much. And more likely it'll be even less than that. But if we have a system where we're like doing, say, land sales, do you care whether or not my land title is valid? Right? Why do you care? It's not your problem. If I'm sitting on land that's not actually mine, it's not actually your problem. It's my problem. I'm the one who wants to own my house. You really don't care who actually owns the house across your street. I mean, the friendly neighbors, you might care who they are, but whether or not they own the house, it's not your problem. Well, so why are you validating that data? Why don't you just validate the data associated with your transaction? Well, what sort of data structure do we need? Finally, this gets to the idea of a single-use seal. And this idea I came up with not so much because it was a new invention, but rather because it was a really good way to talk about what we actually needed. And in a lot of consensus systems that trade things that are not, trade things that are rivalrous, where only one person can own them, what you really want is the ability to have a state machine where what states have happened and you can't replicate a state again. Right? You want the ability to prevent a double spend. So what if you had some magical mathematical thing that was uniquely numbered and you could only close it over a new piece of data once? And this thing would be kind of like the seals they put on shipping containers, right? Those things are uniquely numbered. So, if you're getting a shipping container full of goods from Japan, they can go tell you, oh yeah, this container is going to be closed with this seal, with this number. And when it arrives often, here in Ukraine, we can go look at the number, and provided the number matches, we know that whatever in the thing hasn't been modified. Right? Because you can't open the container without pulling the seal off. Of course, anyone involved in physical hacking will tell you a zillion ways these seals can be manipulated, but if we had such thing in math, that'd be really cool. Right? You could go have a construct, kind of like a pub key with signature, with a magical property that you could only ever sign once. And if you can only sign once, now you have an anti-double spend mechanism. Well, what is an example of a single-use seal in reality? A Bitcoin transaction output. Right? You have a uniquely numbered thing, a TXID, and an output number. You can only spend it once. And when you spend it, you can create a protocol where the way you spend it commits to new data. And first of all, I'll go point out the Bitcoin protocol did not actually have transaction ID uniqueness. We actually screwed this up, but that's being fixed. But the other thing I want to go say is, well, what the hell did I mean when I said commit? Well, commitment is another one of these terms that I think people in the client-side validation communities come up with. I might be one of the first to say this, but basically it's this idea that, what does a hash function actually do? Well, it says that I have this data, and I'm referencing it by hash, and provide the hash function secure, I have committed to the data. So whenever I say commit to this, commit to that, a commitment, whatever, I'm really, for the most part, talking about hashing. There can be some subtle differences, like this is relevant to how open timestamps works, but commit, think hashing. And people say that because the meaning is not really the same. Like hashing, it's the way you do it. Committing is what you're trying to do. So, let's back up again. We have a single-use seal. We have a unique number attached to it. We can close it once. In the process of closing, we commit to new data, and we have some kind of, really a witness, proving that within the system that has happened. Now, we have one example of commitment, a transaction ID. Well, why is it commitment? Because the rules of Bitcoin. Well, why do the rules of Bitcoin work? Ultimately, because of this idea of having a blockchain. Well, what is a blockchain? And I mentioned this in my previous slide. Previous talk. It's really a proof of publication system. We have some medium that everyone has a copy of, and we publish data to it, such as signatures, and we define validity as being the first person to publish a valid signature for a particular event. So, could we leverage this concept to maybe do something more clever with our single-use seals? Like, what if we want to have a whole lot of single-use seals, right? What if we want to have like 1 billion of the damn things because we're tracking 1 billion assets? How do we do that with one Bitcoin transaction output? Well, you can layer this stuff. You can take one level of single-use seals committing to blocks in a proof of publication layer, and then define a valid seal for your secondary system as the absence of a signature to a particular pub key up until a point where a valid signature is published. And the valid signature being published, that is an act of closing the seal. So if I want to prove to you I closed a seal in the system, first of all, you get into consensus with the top layer by looking at Bitcoin. Now that you're in consensus with the proof of publication layer, you check that layer for valid signatures for that seal. And once you find the valid signature, you check that it commits to the data you think it committed to. And now you have a unique action that could only be done once, but the data for that didn't need to be published in Bitcoin. And notably, that data publication layer, you could have like 1,000 people publish in it, right? You could have an unlimited number, and none of that data would need to be on chain. Of course, we do have one more problem, which is we've now created 2 blockchains, neither of which scale. Now, the Bitcoin, we solve scaling by saying, well, it's only a certain size. This other one, though, like we're going to run out of bandwidth at some point if, a million people try to use it. But we can do something clever. We can apply trees to the problem. Because remember, everything in computer science is solved with a tree. Well, we can, rather than having a block, we can define our publication layer being a Merkle tree, where the path down the Merkle tree is determined in advance by some kind of subject matter, such as maybe the first bits of the pub key. So if we have a system where, like, if you look at the pub key that's attached to the single-use seal, and you just get the bits of it and then follow that down the tree, you could say signatures for that single-use seal are only valid at this part of the tree. And at every step of the proof of publication layer that does not contain a valid signature, you need roughly log 2n data to prove the absence of a valid signature. All right? Someone could publish a valid signature in another part of the tree, but by definition, it's meaningless. It's just meaningless data. I could write a valid signature on the bathroom wall. Doesn't mean I closed the seal. It just meant I made the janitor really angry. So, we have Bitcoin, which is secure. We defined a proof of publication layer. We have our single-use seal, a proof of publication layer. We've split it up with a tree. Now, for the length of time the seal is in existence, we need roughly length of time L times log 2n, and then that's how much data we need to go prove. So what does this look like in practice? Well, let's suppose, what's the biggest possible tree you could want? Maybe like 32 levels deep. Imagine you have like 1 billion seals potentially being closed per block, per 10 minutes. That certainly seems to be enough. And if that's not enough, we'll just add a few more layers to it. Well, that amount of data per year, if every 10 minutes, I forget off the top of my head how much it works out to be, but you're talking, hundreds of megs, even if you can close a seal every block. And a lot of these systems, if you're talking about a house registry, you don't need to close every block. It's fine to close, it every day. You're not going to sell a house faster than once a day. So these things actually scale really well. So what can we go build with this? Well, what if rather than tracking the ownership of houses, what if we want to track the ownership of USDT stored by a shady company that refuses to go and let you know where all their US dollars are? I hear that's actually a multi-billion-dollar business. And Tether is very, very popular. But Tether needs a good accounting layer. Because, I need to be able to go trade USDT with you, and Tether doesn't want to have anything to do with it. Well, with single-use seals, we could have a mechanism where when we actually do the trade, I give you proof that a seal has been closed over your new pub key, and I go backwards, showing every step of the way, all the way back to the point where Tether just said, this USDT exists, the genesis state. Now I have something that's kind of like a blockchain, but it's implemented with seals, and how much data is necessary to prove a given output scales with time. Is this useful? Well, if you add Lightning to this, so normal transactions can happen quickly, I think it's very useful. Even though, maybe your history gets a little on the big side going back. But even if the history gets on the big side, because, you merged and split coins, because it's a centralized system, you can always go back to Tether and say, could you just reissue these from scratch? All right, prove that Tether was burnt and then recreated. That's perfectly fine. And finally, I'm not looking at my watch, but I'm assuming I'm running out of time. I'll go take this full circle and say, well, could you do this with Bitcoin? Right? Like, why does Bitcoin have blocks? Why don't we put trees in Bitcoin? And this is another one of those things where, like, I invented something in 2013 that no one's really done yet, is imagine if the Bitcoin chain itself was a tree. And then you can kind of make it a chain of trees, and you can imagine, well, what if, like, different trees had different levels of proof of work? And that gets to this idea I had a long time ago in, like, 2013, called tree chains, where you say all tokens on the system are backed by proof of work, but the security of your token goes down as you choose to have less and less proof of work. And now you get this weird thing where, like, I am proving to you the money is real by giving you the history backwards in time, and then proving it's not double spent through proof of work. And then we can go choose what level of proof of work we have based on your security needs. If you want really secure coins, well, we should have the level of proof of work higher. But the beauty of this is you can go make a system where, like, once the coins are in your possession, you've chosen their security level. I might go lose them because they're so insecure that, like, data gets lost. But once you have them, they're in your possession. And maybe in the future, we're going to rewrite all of, like, Bitcoin to go do this. I kind of doubt this because Lightning works pretty well. But, it is in possibilities. Certainly, I think in the near term, of course, RGB does exist, and you can actually use it in production, so they claim. I own some NFTs on RGB. Also, like, anytime you have a database, I mean, you really should be using something like single-use seals to just commit to versions of the database. Last year I was involved in the auditing of the Guatemalan presidential election, and we used timestamping to prove that ballot tally sheets were created prior to some point in time. And in practice, what that really meant is we could prove, yeah, these ballot tally sheets were created, like, right after the election ended within the time you'd expect them to be counted by hand. That's very good for preventing fraud. And in fact, it might have saved their election because they misconfigured a whole bunch of machines there with the wrong time zone. So it looked like a whole bunch of tally sheets were fraudulent. And then the timestamp showed up and said, yeah, this is actually when we expect them to be created. And that's all cool. But with open timestamps, you could always go timestamp an entirely alternate set of data that's equally valid looking, but it's a total lie. And single-use seals is an easy way to conceptualize how to build systems that fix this problem. I say easy, and I really should put this in quotes, because timestamping is easy technically because it's a thing you add to data, right? You have a chunk of data, you add a timestamp. Single-use seals are much harder because it's something that the data has to be, right? Your entire data structure has to be organized around, kind of from, like, the top down, taking this topic, splitting up this topic into subtopics all the way to the point where you have your consensus-related thing. Long story short is this is hard to do. And right now, I don't really know of good libraries to do this. I tried to make one, like, called Proof Marshal, as in the idea that, we're marshalling proof data around. But after months of work, well, years of work on and off, I've never really come up with a system that's usable. So, maybe someone will come up with something better. Every time I look at the RGB code base, it looks like kind of a mess. But it's a hard problem, so we'll see how that goes. But certainly, if you want to think about hard things, like, this is an interesting avenue of discussion, and it's something where Bitcoin is potentially really useful. And we can do these things in ways that scale, so it's not like you're really putting a lot of extra load on Bitcoin.